So this is our third lecture in Chapter 11 on heat exchangers. We've covered almost all the material, the overall heat transfer coefficient, the analysis method of using the log mean temperature difference, and the other technique using the effectiveness-NTU method. This is the preferred method. I really didn't do a lot on the log mean temperature difference. If you have anything other than a concentric tube heat exchanger, Q is equal to UA with a correction factor for that particular heat exchanger times the delta T log mean. This looks like it would be just as easy to use, but right in here I have to not only know the temperature of the hot end, the temperature of the cold end, I also really need to know the temperature of the hot out and the temperature of the cold out in order to calculate the log mean temperature difference. So the challenge or the difficulty associated with that log mean temperature difference, if you don't know the outlet temperatures, which is often the case, it's often iterative. Where if you get to and use the effectiveness-NTU method, you can see that it typically is not iterative when you don't know the outlet temperatures. It's not necessarily iterative. It's more explicit through the system. All right, so I'm going to spend a little time talking about the U, talking about heating coils, and then talking about a particular application that if you work in the area of HVAC, heating, ventilation, air conditioning, the American Society of Heating, Refrigeration, Air Conditioning Engineers has a lot of material out there, and there are some interesting discussions of the nonlinear characteristics, the nonlinear thermal characteristics of heating coils used to in buildings to make warm air in the winter and supply that warm air to the interior of the building. All right, so let's jump into it. Here's a problem. So we have a shell and tube heat exchanger. It's a different type of heat exchanger, not a concentric tube, shell and tube. What does it look like? Well, in your mind you can think of, oh, I have something going like this. Maybe it's a U-tube configuration. Maybe I have an inlet and an outlet on the shell side. The details are, that's what comes to your mind. Oh, a shell and tube heat exchanger. All right. It has a total area of 12 meters squared. And I'm just going to jump down here, and it has an overall heat transfer coefficient, U, associated with that area of 210 watts per meter squared Kelvin. I have the advantage, I actually wrote the problem, so I know I should have rewrote that. I should have put that information earlier in the problem statement. Let's continue now reading the problem. So you have engine oil. It enters at 60 degrees C, and given flow rate and water enters at 10 degrees C. So I have oil and water. Which of the fluids are hot? Which fluid is the hot fluid, the oil or the water? The oil. And I would encourage you to try to organize it on your paper. So we have that the oil has an inlet temperature of 60 degrees C, has a mass flow rate of 2.5 kilograms per second. The cold fluid is the water. It has an inlet temperature of 10 degrees C and a mass flow rate of the cold fluid to be 10 kilograms per second. Well, with a little work, I can go and I can look up the specific heat of the oil, the hot fluid. The specific heat is around 450 joules per kilogram Kelvin. And the specific heat of the cold fluid, the water, that's around 4,200 joules per kilogram Kelvin. So right away I can calculate the heat capacity rate of the hot fluid, and it's going to be 1125 watts per Kelvin, and the heat capacity rate of the cold fluid, it's going to be 42,000 watts per Kelvin. All right, so I'm already thinking I'm going to solve this problem using the effectiveness-NTU method. What are they asking us to solve for? They want to know the rate of heat transfer that's being accomplished in this heat exchanger. What is Q in units of watts? And then Then also, what are those fluid outlet temperatures? What is the temperature of the hot out and the temperature of the cold out, both of those in degrees C? All right. So let's use effectiveness NTU. If you tried this with the log mean temperature difference, you would definitely iterate. All right. Okay. So we have these. So what would be the next step? Which is the minimum heat capacity rate? What is C min for this problem? Yeah, 1125 watts per Kelvin, isn't it? And if I'm looking to calculate the Q, do I want to calculate the effectiveness or the number of transfer units? Where is Q embedded? Is Q embedded in effectiveness or number of transfer units? Well, what was the definition of the number of transfer units? UA divided by C min. What is the definition of effectiveness? Q divided by Q max. So it looks like I need to calculate the effectiveness because Q is equal to the effectiveness times Q max. Right? All right. What you'll find is the effectiveness NTU method has a bunch of little steps. There are little relationships like this. Like what is the definition of NTU, etc. Okay, so let's go ahead. We can calculate the Q max. Isn't that C min times temperature hot in minus temperature cold in? All right, let me do this. You all have a calculator. Use it. I'm going to walk around. I want to see if you can calculate Q max. And then I also want you to calculate the number of transfer units for this problem. I want you to calculate the number of transfer units, add Q max. All right, I'm going to pick it up here. So a lot of us have this 56,250 watts. Add the number of transfer units coming from here down. Gives us that it's 2.24. And somebody already started working to get the ratio C sub R, which is C min divided by C max. And they found that that ratio C min to C max is 0.027, very small. And now they're ready to go and find the right correlation, the right equation for the shell and tube heat exchanger. So let's take a look. So you can find in table 11.3 where you could get the effectiveness as a function of that ratio of heat capacity rates. It's over here and over here. It's 4 places in this equation, as well as the number of transfer units. You have to read this carefully. They have it's a 1 shell pass and 2 or 4 or 6 or 8 tube passes. So for this one, you can see that it's a 2 tube passes, and you have kind of a 1 shell pass. Look for another correlation if that's not your configuration. Now, I don't like having to use analytic expressions if I have a plot, and the same information is put into a plot. And so this plot, what do they have on the x-axis? The number of transfer units. What are the different red curves? That's the different ratio of C min divided by C max. Professor, why didn't they just put that as C subscript R like they did in this equation? I don't know. They just wrote it out as C min over C max. It's the same thing. The ratio of heat capacity rates. So what we do is we say, well, what was our value of the number of transfer units? Around 2.24, right? Where is that on the x-axis? Here's 2.5, 2.5. Here is half, 2.24. Right? Okay, and then for our C sub R, it was 0.027. Well, it's either 0 or 0.25, 0.5, 0.75, or 1. Let's call it right there. a skosh below the red line. And now let's read off effectiveness. And I'm going to have you read it off and tell me what is the effectiveness for this problem. 0.88. Good enough. Somebody says 0.9. Okay. 0.86. Okay. 0.87. 0.8732. Ah, come on. You don't have that good eyes. So 0.88. Good enough. I'm not going to quibble too much on that. Let's go back. So we get the effectiveness from either the equation or the plot of 0.88. You're now ready to unravel and use this equation. So the Q is equal to the effectiveness times Q max. We calculate it. See, it's a bunch of little steps. And this Q comes in at, well, let's 49,500 watts. I really shouldn't even put it to 3 significant digits. I should say 50,000 watts and call it quits. Because what was our epsilon? How many significant digits was on that? The effectiveness? 2. And yet my final answer is 3. So if you're doing that in an exam, I usually mark it up with a lot of red. Like, hey, you rounded this off to 2 significant figures. Use that later, and now you have it to 6 or 5. You need to be consistent. Keep all the digits in your calcs when you can. All right. Now what I'm going to do is I'm going to stop. I'm going to walk around, and I want you to calculate both the hot out and the cold out. What are the 2 temperatures? All right, so I'll pick it up here. What do we have? We have that the temperature hot out is the temperature hot in, and it's going to be cooled by how much heat is removed compared to the heat capacity rate. Where did that equation come from? Energy balance of the hot fluid stream. And then we're able to calculate that the temperature hot out comes in at 16 degrees C. Likewise, the temperature cold out is equal to the temperature cold in, but it's not, it's a positive Q into the cold, so it's going to be increasing the temperature. And so the temperature cold out comes in at 11.2 degrees C. And again, that's just an energy balance. Let's make some observations about this. Somebody says make some adjustment to the heat exchanger, either flow rate. Which flow rate would you change, and what would you increase it or decrease it? The cold, it's going way too fast, isn't it? You could slow it down some. It'd probably do the same job of changing, of having a similar Q. Oh, it'd reduce it a little bit, but not much, right? Because you could see that it's not picking up much heat in the cold. Anyway, little observations like that. Well, we have a lot of heat exchangers which are cross-flow. You've seen them. We talked about them before. Especially used to change the temperature of air. Air maybe that's supplied to a building, and maybe you use warm or hot water to heat it, or you could use cold water to cool the air in the winter or in the summer. So typically the water is supplied and returned, and then the air goes across. What do you do on the air side? You fin it. Why? The H on the air side is so low. This is one of the themes I really want you to leave this class with. It's kind of hard to get heat in or out of air. Air has a low conductivity, and through the Nusselt number you can see H's are proportional to K. It's going to have a low convection coefficient. Water, just the opposite. Good high conductivity and often a good convection heat transfer coefficient. So that's why you fin the air side of a heat exchanger. How will the overall heat transfer coefficient U change if the mass flow rate of the air is increased? Will it go up Will it stay about the same, negligible change, or will it go down? So I want to pause, walk around. You just answer that question on your sheet of paper. Professor, what was U? How did we define it? Well, think about this. 1 over UA is equal to 1 over HA on the water side plus some L over Ka conduction through the solid material that separates the air and the water. Okay. And then we have 1 over HA on the air side. And we just talked that maybe you have finning, and so you're really trying to boost up that area on the air side because this H on the air side is so low. So there's U, a little reminder. So how does that U change if the air mass flow rate is increased? All right, let's do this. Let's approach this problem slowly. So the mass flow rate of the air is going to go up. Can you tell me about the velocity of the air kind of going across the fin surface? Is it going to go up because of that? Yeah, that's going to go up as well. So the speed goes up. How about the Reynolds number on the air side? Do you think that goes up or down? Up. All right. Hey, you know what? From the perspective of the air, I know you could think about it flowing through passages, which are on the sides by the fins and then the tubes on the top and bottom, or you could think about it as just flowing over a one surface at a time, external flow or internal flow. Internal flow through channel or external flow over the fins, right? So, but our general relationship coming out of convection is that the Nusselt number is equal to a constant Reynolds number to a power, Prandtl number to a power, about a third. Let's call that quits right there. Okay, so embedded in the Nusselt number is my H. So it's a H, let's call it L divided by K. Constant Reynolds number is based on L then. And our Reynolds number is rho U L divided by mu. And then the Prandtl to the 1/3. And I left off that exponent. Now, if it's external flow, a lot of those correlations had an exponent of 1/2. If it was internal, Dietz-Boelter, who can remember in the Dietz-Boelter, Reynolds number to what power? Yeah, 0.8. 0.8. So between 0.5 and 0.8, that's the vast majority of data. Correlations put it. So you can pick one, and let's just pick for simplicity 0.5. I'm not saying it's better than 0.8. I'm just saying it's in the vicinity, 0.5 or 0.8. So we can see that the convection coefficient on the air side is proportional to the speed to a power like 0.5. So if the air side speed went up, hey, we concluded that. We said the Reynolds number went up. That meant the Nusselt number went up. Maybe not 1-to-1, right? Maybe it's a square root of that increase. But what about the H on the air side? It will go up. So if the H on the air side goes up because of the increased flow rate of the air, what does the conduction do? About the same, not changing. What about the water side? We didn't change it. So look at this equation. Area stays the same, area stays the same. This H went up. What does the U do? Has to go up. Oh man, that's a pretty tricky problem, Professor. I agree. I agree. Especially if this is the dominant term, which it often is. This term not only is constant, it's negligible in the equation. And not only is the H so large for the water side, that makes that term negligible, such that it's a 1-to-1 increase. If H goes up by a factor of 2, U goes up by a factor of 2. All right. Do I want to play with this again? No. Fine. We'll call it quits. Oh, did I finally answer this question? Yeah, so if the mass flow rate of air goes up, what will the U do? It'll go up. All right, let's press forward. Take a look at this table, 11.2, they have representative values of the overall heat transfer coefficient in these units. And you got water to water, water to oil. Those are pretty good values. The oil may be a little lower conductivity, hence it's a little lower, right? U for water to oil. Here you have steam and condensing and water tubes, ammonia condensing, alcohol condensing. Those are all pretty good, pretty high. What's the low one on the chart, on the table? Why is it low? Is it because of the water in the tubes? No, it's because of the air. Anywhere there's air, it's a low H, and that's it. That's a low. Going to give a low U. All right. So not only do mechanical engineers study heat transfer, but also chemical. And I grabbed this out of a chemical engineering design book, and I thought it was pretty good. And it takes us a while to understand it, but let me try and do this. In chemical engineering, they often have two fluid streams. One they may call a service fluid, and the other they may call process fluid. I'm sorry, I'm not more up on the lingo, but that's their terminology. And you can see that maybe over there they have a boiler or a cooling tower. Let's say they have a cooling tower, and the cooling tower is supposed to provide a service fluid, and the service fluid is supposed to affect the process fluid, maybe something that like organics or paraffins or salts or oils, something that may be a valuable product, something like that. I'm just trying to talk through this. So let's say they have cooling tower water. Well, this person put this together and said, you know, the coefficient, look at the units. It's like the H on that fluid side, watts per meter squared degree C. Sorry, it's not larger font. Probably those in the back can't read it or see it. Can you see it back there? Yeah, I know, pretty hard. But it's in this range. Now on the other side, let's say you're using this cooling tower water with this range of H to do something with oils. And the oil has a range of H right in here. So if it was this particular H on that side and this particular H on that side, you just draw a straight line between. This is really old school. This is before computers. Actually, engineers were able to do things before computers, believe it or not. And this is often the way they did it. It's where it crossed another line, which was our overall coefficient, cap U, in units of watts per meter squared. So it's like, oh, this one comes in, if I'm just trying to read it, there's 250, there's 500. Looks like it's the 3.5 or something. 350. See how they do that? You know, if you change it up and you say something like is condensing, right? Condensate. And you have some, I don't know, boiling, organic substances, you can get some pretty hefty, pretty large values of U. But every now and then your service fluid may be air. A gas. Where is air or a gas on that axis? Oh, wow. Look at that. You need to, in the back, you really need a microscope, right? To see this. All right. What happens if our process fluid is air or a gas? You're trying to move from air or gas to another air or gas. Guess where air and gases are? I don't care how I draw a straight line between that region and that region. Am I going to get a U out in this region? No, this is the beauty of something graphical. It's like you're stuck. So let's say air is down here and you've got something that's good. Well, that's great. You've got something that's good, but you're still confined, you know, to the lower corner. You're still going to have a low U. All right? Or if the process fluid is a gas or air, no matter what your service fluid is, you're stuck. Just reinforces the same idea that I want you to leave this class with. Now let's think about a very common challenging problem. It's out there. If you're in the HVAC industry, heating, ventilation, air conditioning industry, you're trying to make air warm in the winter so it can keep the buildings warm, or you're making it cool in the summer so that you can provide air conditioning cooling to the buildings. So if you have what they call a heating coil, maybe you put hot water through that heating coil in the tubes, you know, in and out of the tubes, and then the air goes across, and they even color-coded it. Look at that. It's red. That's a little warmer. But they color-coded down here. In the summer, you may have chilled water, cold water going in and out of the tubes. That's what we have on campus. In our mechanical rooms, we'll have heating coil, and then close to it, somewhere else, will be a cooling coil. And it'll supply cold air to the building, interior of the building and rooms. Now what happens is the airflow rate is very constant throughout the year. Because if they modulated that a lot, what would happen? You'd go into a room and you'd feel stale air. It's like, hold it, I need to have some outdoor air mixed in and continuously circulated into the building. So what they end up doing is they modulate, or they change the flow rates of the water, or of the hot water, or of the cold water. And often the supply temperatures, the cold water coming in or the hot water coming in, are pretty well fixed. They're pretty well fixed, right? But they're going to start tampering with or changing the flow rate, the m dot of that hot fluid in this case, or the mass flow rate of the cold fluid in that case. Guess what? You're equipped now to really understand something that's interesting. So let's press forward here. When they have a heating coil, you could do this also for the cooling coil, but especially for the heating coil, you'll have some hot water come in, and you want that hot water to come out, and they'll distinguish a certain, or the design engineer will pick a supply temperature. In the South Energy plant, I think it's 180 degrees F. They don't want it to boil. They want it just hot water in, hot water out. And I think it's only a delta T of about 20 degrees F. The design engineers picked this. So guess what? It goes out at 160 F. That's the design. This is to run on the coldest day, cold day in this city. That's what the design. You go up to Chicago, well, they're going to have a different cold day design for their buildings. All right, so the airflow is sort of stuck, and you don't want that air to come out too hot. So maybe it's going in at about 70 degrees F, and maybe you want it out at 95 degrees F. You don't want it out at 120. It'd be really uncomfortable for the person sitting near where it's dumped into the room, especially if it didn't get well mixed before it started to get into the occupied space where people could feel it. So they design it, and then they install it. But how many days of the year is this thing running full tilt? Just because it's winter doesn't mean it's the hardest, coldest day of winter. A lot of times it's winter, but you don't need all that amount of heating supplied. So the boiler doesn't change the temperature. The return air doesn't change the temperature. The supply air, we don't really want to change that temperature, but what starts to really change is that delta T across. So anyway, what they found is if you just put a valve right here, and you said, okay, start turning that valve down, closing it, closing it, closing it, to choke off the hot water flow. Airflow rate's the same. What will happen is you'll go from 100% design on the hot water flow to 90%, to 80%, to 70%. This is of the mass flow rate of the water. You would think, or you would like, the total Q removed from the hot fluid and put into the air would go down proportionally. So that if you reduced it by 90%, Q would be reduced by 90%. But au contraire, no, no, no. If you have a 20-degree delta T for your design of your system, let's say you reduce it by 10%, what is the reduction in the Q? Can you kind of see that? It may go down by 2%. All right, turn it down some more. 20% reduction doesn't go down by 20% in the Q, it goes down by 5%. So this is a nonlinear response. So finally, We can puff up with little pride that heat transfer has some curves that are even close to the mathematical elegance and sophistication of the dynamics people and the vibrations people. Remember that? The overshoot, undershoot, and all that. The whole class has just been sort of boring, exponentials for us. Sorry, right? Apologize, right? It's kind of first order. Thermal systems are essentially first order. There's really no overshoot, undershoot. I know you all semester you've been disappointed. All right, but this is if you have a 20-degree design change. Now, why does the UTSA plant really focus on 20-degree? Because they don't want it so cold when it goes back to the boiler. It's easier just to recirculate a lot of water, let it be 20-degree difference. Somebody says, why don't you have a 60-degree? Okay, well, if you do 60, then it's coming back 120, and it's going to be a little more mixing of cold water coming into your boiler, and the boiler designers don't like that. It's something about thermal stresses and that. All right, but it would be less nonlinear if you had a larger delta T. But let's just focus on that 20-degree. Okay, so the story is when you have a valve up here, I'll give you the bottom line. Engineers know this. So this plot is out there in so many books and so many documents that it's almost like, wow, there it is again. Oh, look at that. There it is again. It's very common to have this explained, that the design engineers or the manufacturer have put together nonlinear valves such that when you turn the stem of the valve 50%, you got a whole lot more reduction in the flow rate than just the 50%. Or if you turn the stem of the valve by 10%, you get a lot more reduction in the flow than 10%. So that they kind of come in here with a very rapid knockoff, such that if you combine this nonlinearity with that nonlinearity, the percent turn on the valve would result in a net percent reduction in the Q transferred in that heat exchanger in a one-to-one relationship. It would be more straight, easier to control, less sensitivity. It would be the equal sensitivity throughout the range of the valve positioning. So that's how they solved this problem. But let's understand it because we have all the math to understand this. We can go in, this is what I did, we can just pick some temperatures both in degree F and degree C. Degree F, degree C, this would be for the cold air. And then for the water, we'll do the degree F, that's a 20-degree F change. That'll be our design. You can see it in degree C. And we can go and say, oh, this is a cross-flow, single-pass, both fluids unmixed heat exchanger. There's our analytic expression for NTUs and effectiveness, or the same information plotted. And we can analyze this problem and do a pretty good job. So I set it up in Excel. You could set it up in Excel. You have just parameters associated with water, parameters associated with air. What we're going to do is we're going to come in and change the mass flow rate of that water. We're going to start cutting it and then re-solving this problem, Excel, and then plotting the results. So the air flow rate we're going to leave fixed. The air U and the A is going to be fixed. I know it could make it more complicated by changing the U, but let's leave it alone. And you could see the method implemented. So this equation's implemented. Well, what about the results? This is what we're trying to reproduce. A famous diagram out there in the literature. Here it is in Excel, those equations just shown. So this is the fraction of the water flow rate from 100% down. What is this? The fraction of the Q transmitted in that coil from 100%, and how's that for a match? I don't know where they got this data or plot from originally. It could have been empirical, but things get repeated so often it's hard to actually trace it back to who did the first plot and where did it come from. But this is a reproduction. You can see the nonlinearity. What happens to the outlet air temperature? Well, if I start to curtail the water flow rate, it really doesn't change it or knock it down much until I really get, then it's going to be colder air coming out across that coil. It won't be 95F air coming out across that coil. Okay. You could then take a look at not only the air outlet temperature, which was on the previous slide, and this is where you get some neat plots, right? Hey, we're getting pretty sophisticated here. Let's take a look. This isn't just a boring exponential anymore. This is the water outlet temperature. So as you used to have it would come out at around 80 degrees C, right? What did it go in at? 5/9 of 20 degrees higher. I forget what it was. It went in at, what did it go in at? 91. All right? So the cooling water went in at 91. There was a drop down to about 80, but if you start to throttle it, you'll get a larger drop, a larger drop, a larger drop. It'll come out cooler. Okay? There's less of it, and so there's a more temperature reduction in that hot water. You could also look at the minimum heat capacity rate. Why is it flat until I get to a certain flow rate? Why is the minimum heat capacity rate constant at whatever this is, 2,400? Can you explain why that's flat? What is this again? C min, the minimum heat capacity rate. Because it's the air. And then finally, what happens at this point, as I continue to reduce the mass flow rate of the water, finally the water is now at the minimum. And as I reduce it, it's a 1-to-1. As I reduce it. How about the number of transfer units? This is harder. The number of transfer units is UA over C min. Well, U and A aren't changing. C min, and then finally C min starts to really get smaller, and so it picks up for the number of transfer units. Aren't these pretty sophisticated curves? You're not impressed, or you are? Come on, be impressed. But look at that. Wow, finally something on order of the vibrations and oscillation and harmonics and vibration and all that. So anyway, here is, you're reducing the flow rate of the water. You have the ratio, C sub R. It peaks at 100%, right there where it's switching between the minimum is the air side and now the minimum is on the water side for the minimum heat capacity rate. And then this one is the effectiveness, epsilon, and it's pretty flat. And then finally you have an increase because the effectiveness is Q over Q max, and this Q max is being reduced a lot, and Q is getting closer and closer to Q max. Well, anyway, this is a very popular curve. It's in a lot of books, and with the skills that you've developed in this class, you not only can understand it, you can reproduce it. Well, with that, I have wrapped up this chapter, and I'm going to stop now and give you a quiz, and then we'll call it quits for the day. Thank you.